There we go. All right, so one more time. There are 3 parts to this chapter. And so let's look at the first part again. Yesterday, I'll do a very fast review. There we go. I'll do a really quick review of yesterday. There you go. All right. So we found out that there, even long ago, the Greeks, they thought about, hey, what are things made of, you know? And they thought everything was made of only 4 things. Do you remember that? Do you remember the 4 things they thought everything was made of? Okay, it's right there. So if you haven't read this yet, you can look at it. And what was it again? Water, fire, earth, air. Okay? Anyway, and then at that same time, there were people who were talking about, yeah, but what are things really made of? And some people thought that matter was infinite. You know, if you go down and chop pieces of copper in half forever and ever and ever, it's still going to be copper. That's what they thought. Well, that was okay. Unfortunately, though, I never see their name in a chemistry book. Wonder why. And then Democritus said, I don't really know why, but I just don't think it would be that way. I think there would be, if you keep cutting in half, you're going to get to a point where you can't divide it anymore. It's going to be indivisible. And what was that word that meant indivisible? What was the word? This is review, okay? This is review. This is where you kind of fill in the gaps. What was it? Atomos, right. And that's where we have the word atom. So the atom came from this, and that's why his name's in there, because that's what we believe is happening. There is a piece called that. Now, we did find out later, though, that you actually can divide atoms. At one time, we thought, okay, they're indivisible, and they're called atoms, so we call them atoms. But we now know you can actually split atoms. And by the way, if you do split a copper atom, it's not copper anymore. Got that? Then we down here, and almost a 2,000 year period where people were trying to change one kind of matter into another. And it wasn't the same person. You got that? 2,000 years? They would have passed on their information from generation to generation. And some of them, honestly, were very good scientists. They developed acids, discovered elements and glassware. I think they really were the precursors to modern science. But I think some of the alchemists, some of them were out to make money, some were out to cheat people, some were out to praise God and try to change things into gold. I think they did. They did that. So anyway, then you get into the Renaissance. Everybody, you guys do that in humanities, don't you? Talk about Renaissance. I thought all humanities classes did something like that. And you say that there's a little bit of a change, and science is getting a little more organized, a little more modern. And you see this guy here, Robert Boyle. And it said here is best known for his work on gases. That's true, Boyle's law. But it also said his most important contribution was that science should be grounded in experiments. And they didn't have that before. Before, it could have even been superstition. But they're going to say, if you can do an experiment and show me that, then I'll believe you. And so that's where kind of modern science started coming around. Now, he also did other things. He did... said, you know what, we got to figure this out. You think everything's an element. We got to stop doing that, you know? We got like hundreds and hundreds of elements. Are they really elements? So he did come up with a definition. He said, if you can break something down into simpler things, then don't call it an element anymore. But if you can't break it down into any simpler, then, all right, we're going to call it an element. And I know water was an element for quite a while because they never did learn how to break it down. Then they did. They used electricity, and they learned how to do that. And now they knew water was not an element. It was made of something even simpler than that. Do you like me to review like this or not? Would you rather just go on? All right, the review is where you're supposed to fill in any gaps you had from yesterday. Okay, so that was that. Now we're going to move on a little further. I won't spend very much time on these 2 pages because the author thinks that you have never had to learn elements. So he gives a list of elements and things like that. The only thing I thought was kind of neat, was that if you had this chart here, it says, what are the most abundant elements found in the non-living world? In the non-living world, what are they? And look at that. There's a lot of oxygen in the non-living world. Some of it's in the air, but a lot of it's in rocks, isn't it? Like calcium carbonate is CaCO3. You could get oxygen out of chalk. And that's what they're talking about going to the moon. water is pretty heavy. And if you have to use a lot of fuel to take a lot of water to the moon, that's going to be bad. But there actually are compounds on the moon that contain hydrogen atoms and oxygen atoms. If we could get those out and combine them, we could actually make water. Make water out of rocks. Sounds weird. Anyway, I think it's pretty interesting. What's the second one? What's the second most abundant thing in Earth's crust? Silicon. See silicon? I don't know if you knew this, but silicon and oxygen together make silicon dioxide, which is quartz. It's sand. A lot of sand is made of silicon dioxide. Okay, then they have aluminum, and then we have iron and blah, blah, blah. But what's kind of interesting is, let's go over here. What about living things? And I'm not your biology teacher, but when I did used to teach biology, I used to tell them that there were 4 elements that are found in the most abundance. Living things, what are the top 4 elements found in living things? And they spell out CHON, don't they? Carbon, hydrogen, oxygen, and nitrogen. When you were studying in biology, different kind of biomolecules, remember biochemistry? She might have called it biochemistry. There were proteins. What are proteins made of? C-H-O-N. What about carbohydrates? C-H-O. What about fats? C-H and a few O's. And what about nucleic acids? C-H-O-N-P, phosphorus. So you see that the living world has all non-metals. Ooh, that's interesting. All non-metals as their top elements. And you'll learn later that non-metals, when they form bond with non-metals, they're called covalent bonds. Whereas the rock, this world, is almost all ionic bonds. Metal, non-metal. Metal, non-metal. So that's the one thing that is different about these charts is, and we know oxygen's still at the top of both those, isn't it? Oxygen's at the top of both those charts. So I won't spend too much time there because they just want to tell you about elements, and elements can only have one capital letter or one capital letter, one small letter. Okay, let's move on. All right, who's this guy? Who is this guy? You know, if you ever wanted to read a little bit about somebody, this is not like some scientists. Some scientists were born and they were in a wealthy family. Some of them were part of nobility. They had a lot of money. This guy didn't. He was actually a teacher, and I don't know how he did this, but he was actually, besides teaching, he actually had time to do science. And his name is John Dalton. And his year, somewhere around 1800 when he did a lot of his good work here. And anyway, so what Dalton did is he did a lot of things where he combined chemicals and weigh them and combine them and weigh them. And then he thought about things. And one of the things he thought about is this right here, the law of constant composition. And what he did was he found out if you give me a little bit of water and I break it up, I get this many grams of hydrogen, this many grams of oxygen. What if you give me more water? I get more oxygen, more hydrogen, but guess what? They're in the same ratio. So he eventually figured out that water is always made of 2 parts H's and 1 part O. And that's what's called constant composition. He found out water's never made H3O. It's H2O, carbon dioxide, CO2. Well then, he didn't have to do this, but because people didn't know about atoms, I mean, they didn't know about anything about matter, he said, I'm going to take the work that I've done and the work from other people, and I'm going to make a statement. I hereby call it, and I don't know if he didn't really call it Dalton, he just said, here's the atomic theory by John Dalton. Okay, ready? So the atomic theory is about atoms, isn't it? Let's take a look at number 1. What I'd like you to know is, do we still believe this today? Number 1, he said, I believe that elements are made of tiny particles called atoms. Do we believe that? We do. Everybody get that? Number 2, all atoms of a given element are identical. Now, he was actually he was on track there. He was on track. It's true, yes and no. It's true that all carbon atoms do have 6 protons. All hydrogen atoms have 1 proton. They are identical in that sense. But at that point, there was no way he could know about, what about hydrogen, what kind of hydrogen is different than another kind of hydrogen? What are they called? We did that yesterday. We had some hydrogens that had no neutrons, and another hydrogen had one, another that had two. What are those called? Isotopes. So we couldn't have known about isotopes, and actually nobody in the chemistry world knew about them at that time. And they also didn't know about a thing called ions. We'll talk about ions today. But for the most part, I'm going to say yes, except for ions and isotopes. Okay? 3, the atoms of a given element are different than those of other elements. Would you say carbon atoms are different than hydrogen atoms? What makes them different? What's the one thing you're sure makes them different? Yes, for sure. For sure. I could even have 2 atoms have the same number of neutrons, but they wouldn't have the same number of protons. They'd be 2 different elements. You get that? So we believe that. And also he said, atoms of one element can combine with atoms of other elements to form compounds. These given compounds always have the same relative types, and that's that law of constant composition. You get that? And I know that sounds easy now, doesn't it? They even teach that in elementary school. But nobody knew that. Nobody knew that. And what I really like is number 5, atoms are indivisible in chemical processes. That is, atoms are not destroyed or created. They simply get rearranged. Now, nobody knew that for sure. How did you know that atoms didn't break apart into half atoms or something like that? You get that? We didn't know that. But he figured that out. And do we think that's true? When you did biology and you had carbon dioxide and H2O, and something happened to them in a leaf and turned into C6H12O6 plus O2, were any atoms destroyed? Were any atoms created out of nothingness? Or were they simply rearranged? And they were. They were rearranged. In the case of photosynthesis, they were rearranged into a molecule that had high energy bonds. And that's why glucose is food. And carbon dioxide and water is not food. Okay. What do you think? John Dalton? All right, I'll do one more. I'll do one more scientist, and then we're going to move on. Let's read right here. It said here, Dalton's atomic theory, proposed around 1808, provided such a convincing explanation for the composition of compounds that it became generally accepted. Scientists became to believe that elements consist of atoms and that compounds are a specific collection of atoms bound together in some way. But what is the atom itself like? It might be a tiny ball of matter that's the same throughout. Maybe that's what atoms are. It might be a tiny, it might be like a ball bearing, or it might be have parts to it. It says it might be made up of a number of subatomic particles. But if the atom contains parts, there should be some way to break the parts up. Anyway, those are just questions they had. They didn't know what atoms were. And then I'll talk about one more scientist, and we're going to move on. What happened next, and I think this is unusual, this guy named J.J. Thomson, this is the late 1890s, okay? Late 1890s. He said that atoms of an element can be made to emit tiny negative particles. He knew that they had a negative charge because he showed that they were repelled by a negative field, negative field. He then concluded that all types of atoms must contain these negative particles. So we give credit to J.J. Thomson for discovering the electron. I'll show you a little picture of this one. Now, this is what I think is unbelievable. Where did his science take him that he thought, I got to get somebody to make me a tube of glass. And I want this glass to be strong enough so if I want to take a lot of air out, it wouldn't collapse. And then I'm also going to tell him I want 2 discs of metal to be in there. And I also want wires attached to the metal. And I want the wires to be sealed in the glass. And then I think I'll hook up the wires to some electricity. Well, first of all, how did he get that far? How did he get to this point where he thought, that's gonna make me discover something? Where'd that come from? As a matter of fact, in 1890, I don't know if you ever thought about this, but they did not plug things into the wall. Did they have electricity like we do? No, for a long, long time, the only electricity people knew was lightning, like Benjamin Franklin, that kind of stuff. And then they had these machines called static electricity machines. Okay, that was nice, but it was static electricity, and you couldn't keep it going, that kind of thing. You're going to see a video later, also in about a week, where it's a reenactment of something that happened. This guy named Alexandre Volta. Get it? Volta? Okay. And he actually put some chemicals together and made a little sandwich of metal, cardboard, and he made this sandwich and he soaked it in some salt water, and by itself, it would produce electricity. And so, wow, that astounded the scientific world. And they made batteries, and they made bigger batteries. They made a battery that was big as this table, all right, sometimes bigger. And then, now I can do some stuff with electricity. And then later, it was much later, in the early 1900s, that's when, you ever heard of a guy named Nikola Tesla? This idea of electricity, he liked that, and so did Thomas Edison. Remember light bulb stuff? You know, remember how many inventions Edison had? They were cranking out inventions all the time, right? Well, Tesla actually worked for him. But there was a little argument that happened. They were trying to produce electricity, and Edison had always done this thing called direct current. So when you turn the crank or whatever you did, it made direct current. And what happened is the direct current couldn't be pushed very far, so maybe half a mile. So I need a power station. If I want a whole city to have electricity, I need a power station, another one half a mile away, another one. My whole city would have power stations in there, get it? Tesla said, there's another way to generate electricity, and it's called alternating current. And if you use alternating current, it'll go miles, hundreds of miles. But Edison was already kind of famous, and whether you call it pride or whatever you want to call it, he said no, Tesla, you're wrong. Okay, Tesla ends up quitting him, but guess what? Everybody on the planet, what kind of electricity do we produce everywhere on the planet? I'm going to go to India, and they have a generator, like Duke Power, right? What kind of electricity? Alternating current. The whole world uses alternating current. Oh, well. And even in New York, the biggest power company is called Con Ed, Consolidated Edison. Even though it's called Consolidated Edison, guess how they generate their electricity? Alternating current. Oh, well. If you want to read a little bit more, it's very interesting to read about Tesla and Edison. Okay, let's get back to my story here, okay? So he makes this thing, it's called a CRT. CRT is a cathode ray tube. Not you, but your parents, when they were younger, they had a cathode ray tube in their house. They probably had more than one. And they called them TVs and computer monitors. TVs now are flat. Ask your parents, were TVs always flat? No. When I was a kid, the TVs were big. In the back of that TV was a cathode ray tube. And what it was doing, it was shooting electrons this way. And the electrons would hit the front of the screen and say, glow, don't glow, 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 don't glow, don't glow. And that little electron gun would go, and it would write the picture many times a second. And all of a sudden, I saw Andy Griffith in black and white. And then they figured out they could put 3 electron guns back there, and in the front have a red, blue, and green up in the front, yellow. And anyway, then they could make color TV with 3 electron guns. Okay. And then they figured out you could do it differently. And you guys have what, LEDs? What do you have, LEDs, or what kind of TVs do you have? Plasma TVs? Okay, but you guys don't have cathode ray tubes anymore. And ask them about their computer monitors. Look how flat that is. Ooh, that's nice. Right? They used to be big hunkamunkas, okay? If you still have one of those in the attic, and if your parents give you permission, the way this works is I need to have mostly a vacuum here. All those old TVs and old computer monitors are vacuums. If you were to lay out a tarp and your parents had permission and you wore goggles, you could take a sledgehammer and hit it or throw a brick in it and it would implode. If you broke that glass, this air pressure would rush in there and boom, like that. It's pretty neat. Anyway, those are the old days, but here's what happened. He hooks this up to electricity and a beam appears in this cathode ray. It's called a cathode ray, all right? And nobody knows what it is, but he was a scientist. So what he did is he hooked up an electric field that had a plus and minus to it. And the beam, it used to go straight. You could actually make the beam bend. You could bend the beam. And the beam seemed to be attracted to the positive and be repelled from the negative. So what did they think? What did he think this beam was made of? I'm looking at everybody's half faces. What do you think the beam was made of? It was repelled by a negative electric field. It was attracted to the positive part of the electric field. What do you think? Okay. What do you think?
Electrons.
Why?
Because electrons are negative.
Right. He didn't actually know what the name was going to be, but he knew there was something negative. So here's his thinking. Ready? This piece of metal, if I put electricity on it, something in those atoms, I can chase them out. I can push them out. And they're going to jump from there to there. And whatever they are, they're negative. And he said, you know what? I think the atom has at least part of its nature is negative. You got this? Before that, we didn't know that. Nobody knew atoms had plus and minus things to it. They didn't. So this is an experiment that was done. And you're right, he discovered electrons. All right. The next thing I want to do, I won't spend very much time on this, is look at the periodic table again. We did this yesterday. First thing everybody should know for the rest of the year. For the rest of the year, you should be able to look at the periodic table and say, where are the metals and where are the non-metals? Can everybody find those? I'm on page 91. Look at 91. Does everybody know where the metals are? There are a lot of them. There are a lot of them. Look at them. Whoa. Whoa. And then the nonmetals are in this little corner here, including hydrogen. And then what about the ones that are along this little stair step, not counting aluminum or boron? They're called what? They're kind of in between, what do they call them? Metalloids or semi-metals. I like semi-metals, all right? All right, does everybody know what they do with semi-metals? In Silicon Valley? Oh, Silicon Valley. What do they make in Silicon Valley out of semi-metals? Yes, semiconductors, all right? Computer chips, don't they? Semiconductor industry is the computer industry, isn't it? All right, let's turn the page, and, oh, I went the wrong way. Oh, went the wrong way. Okay, and again, you don't really need me to help you with this, but here's the periodic table. And just to help us communicate a little bit, everybody knows where metals and nonmetals and semi-metals are. Is that right? Now, you'll find out later that this group of nonmetals, I think they should have their own group. These are called the noble gases, and they don't like to do anything with their electrons. They're kind of inert. Okay, that's it. And right next to them are called the halogens. Okay, the halogens are all the enes, fluorine, chlorine, bromine, iodine, acetine. Okay? Then you go over here. These are metals, but these are called the alkali metals, the most reactive metals of all the metals on the periodic table. All right? Then right next to them are sort of reactive. They're called the alkaline earth metals. You have a big old block here. Those are called transition metals. And then last but not least, the real periodic table, all of this would be pushed down. And this would be right there, 57, 58. See that? These elements follow lanthanum, and they act like lanthanum in chemistry. They're called the lanthanides, or some people like to call them the lanthanoids. Okay. And these follow actinium. They're called the actinides, or this company called them the actinoids. That's it. Those are the parts of the periodic table. So if I do ask you about it, I said, everybody look at the alkali metals. You'll say, I know where that, like that. So I'm going to put this book up for a minute. And what I really want to do is go back over our packet that we did. And again, I know it's Friday. I know that. I know it's the last period of the day, isn't it? I know that too, but let's get going. We can do this. We can do this for another 25 minutes, something like that. All right. You know what I'm going to do right now. I'm going to review, aren't I? If I review last day's lesson, you fill in the gaps. You fill in the gaps, and then we'll do new stuff. All right, let's start with atoms. If you can separate the world of mass from the world of charge, you will be very successful. If you try to mix them, you'll get confused. All right? What I'm going to do is I'm going to tell the entire story of the world of mass, and then I'll get to the world of charge. Are you ready? Here it goes again. In the world of mass, atoms are made of smaller particles. They're called subatomic particles. And we found out that protons have a mass that's incredibly, incredibly small, 1.67 times 10 to the minus 24th grams. Man, it's small. We also found that neutrons have a mass almost the same. Almost the same. It's blah, blah, blah times 10 to the minus 24th grams. But electrons had a mass that was so tiny that it's like nothing. It's like nothing. So being human as they are, they decided to say, I hereby declare that that many grams is now known as something else. That many grams is known as what? Who knows? Raise your hand if you know what it's called. 1, 2, 3, 4, 5. All right. What do you think, Jonathan? Atomic mass unit, AMU, right? So if you read the book and it says AMUs, that's not very many grams, is it? So they said, we're going to call that many grams 1 AMU, and neutrons, you're 1 AMU, and you are like 0.0005. It's nothing. You're 0. So in the world of mass, I won't be talking about electrons. So now let's go visit an atom, and we find out that, wow, the things that have mass are in the nucleus. So if you're trying to study the world of mass, you're studying the world of the nucleus. Yes? So if I ask you about the mass of an atom, don't think about electrons. Go right to the nucleus, and let's take a look at it. I have a mass of 1, 1, 1, 1, 1, 1, 1. So what's the mass of this atom? 7. That's called the mass number. The mass number is the mass of that particular atom. It means how many things are in the nucleus. Now, of those 7 things, how many are protons? 3. We know that that is what distinguishes one element from another. I promise you, if you go anywhere in the universe, if you find an atom that has 3 protons on it, it must be number 3 on the periodic table. It must be lithium. Every lithium atom in the universe has 3 protons. Not 4, 3. It's like a fingerprint. All right, so the atomic number is the number of protons, and the mass number is number of protons plus neutrons, right? Is that pretty easy? What do you think? Pretty easy? Okay. How do we write this? If I wanted to write the symbol for this atom, I would write Li, and in this corner, the atomic number would be 3. See that? But what goes up here, this is the world of mass. The mass number is 7. Everybody see that? So if I had to write a symbol for that atom right here, I'd look in the nucleus and I'd write that. All right, now what if I had an atom which is the same except 1 less neutron? Would it still be lithium? Yes, because it has 3 protons. But now I'd have to write it like this. You're still lithium, but now you're the isotope lithium-6. This is the isotope lithium-7. Every atom in the universe is an isotope of some element. You get it? All of them are some kind of isotope of some element. All right, are you okay on this? All right, we're getting down there. Now let's turn the page. That's not here now. We did this yesterday. And we see 3 different atoms, but wait a minute, it's 3 different atoms, but atomic number 1, 1 proton, 1 proton, 1 proton. Whoa, you all have the same atomic number. You must be hydrogen. You must be hydrogen. You must be hydrogen. What's your mass number? What's your mass number? Only 1 thing in the nucleus? 1. 2 things in the nucleus. Here's your neutron. 3 things in the nucleus. Neutron, neutron. Okay, see that? Anyway, and all those are hydrogen. If you wanted to react them with fire, they would all be explosive. If you want to make water, you can make water with them. Chemically, they're identical, but not physically. They actually have some that weigh more than others. Isn't that right? And what do you call atoms of the same element, but they have different masses? What do they call them? Isotopes. Now, I do want to show you one of the harder topics. Here's one of the harder ideas. And if you look up on the periodic table, you'll see over there where hydrogen has a number 1. That red number 1 says every hydrogen atom has 1 proton. Got that? But there's another number up there, 1.0079. Everybody see that? What's that all about? What's that? What is that? What is it? Yes, Now, if you gave me 1 million hydrogen atoms and I sampled them, and we have a thing called a mass spectrometer, which can actually separate isotopes, that kind of thing there, right? So they're an expensive machine, but it can do a whole lot. Anyway, look at this right here. About 999,900 of the million would be these kind of hydrogen atoms right there. And then maybe about 7 might be like this, and maybe 2 or 3 would be like that. So let me ask you this. If you had 1 million quizzes, and 999,909 of them, you scored a 1. And then you had about 7 of your quizzes, you scored a 2. Woohoo! And then about 3 of your quizzes, you scored a 3. Woohoo! Okay. Darn it. Okay. Now, what would your quiz average be? It'd probably be about 1.079. Why? Because you had so many 1s. But what day did you score 1.079? Never. Think about this, right? That number up there is not the mass number. The mass number for hydrogen is either 1, 2, or 3. That's an average mass. If you gave me 1 million of those items, the average mass of those hydrogen atoms combined. You get that? Are you with me or not? I gotta stop here. This is called the atomic mass. It's the average atomic mass. And there are no hydrogen atoms with that mass. There are no hydrogen atoms with 1.00797. None. There's some, a lot of them that have a mass of 1, a few that have 2, and even a few that have 3. I'll give you this. I don't know why. This stumped a lot of people in the other class. Let's see if it stumps you, okay? Look at chlorine. I happen to know there are only 2 isotopes of chlorine that we've ever discovered. Some of them have a mass of 35, and some of them have a mass of 36. What do you know about isotopes of chlorine now? Who wants to raise your hand if you want to take a chance and try to answer that? Yes, go ahead. They have what now?
They have 29 neutrons.
Well, actually, one of them, I like what you're doing. So the ones that have a mass of 35, okay? 35 minus 17 is 18. So those would have 18 neutrons, but the other ones would have 19 neutrons, right? So we do know that. But if I look up here at that decimal number, it says about 35.5. 35.5. 35. 36s. The average is 35.5. What does that mean? What do you think?
There's close to an even number.
Yeah. About half of the chlorine atoms in the universe are 35, and about half of them are 36. But look at hydrogen. Is that the case there? Why is the average so close to 1? Because almost every one of them has a mass of 1. These are the only isotopes I know of that have special names. We know there's proto means the first, protium, deuterium, duet, 2 people sing, deuterium, 2. Tricycles have 3, get it? Of the 3 isotopes, only one of these is radioactive. It's called tritium. We use that in making bombs, whether you like that or not. We actually use tritium in bombs. As a matter of fact, you gotta sample. You gotta get a lot of hydrogen atoms to get a lot of tritium, because there's not out of 1 million. There may be a couple. You better start gathering lots and lots of hydrogen atoms before you can find a lot of tritium. All right, what do you think? All right, are you guys just being nice? There we go. You're tired and nice. Thank you. Let's go over here. We're gonna crawl over that wall. Okay, we're gonna crawl over the wall, and we're gonna get into another world. Another world. Okay. Now when we visit the atom, oh, by the way, I'm going to be over here now. The world of mass is the world of the nucleus. It is the world of isotopes. Get that clear. That's on that side of the brick wall. You get it? Don't say the word isotope over here. You get it? We're not going to say the word isotope over here. Over here, you're not going to tell me about electrons. Over here, you're not going to tell me about neutrons. Because in the world of charge, if I went down and visited atoms and I found a particle, whoa, you're charged. Whoa, you're charged. You're not. Who had no charge? See that? And they both got some ice cream, and Mr. Greer was there, and he said, for you, that'll be $4.50. And for you, neutron, no charge. But anyway, sorry, I just thought I might wake you up a little bit. Because neutron, no charge, no charge. Well, anyway, the neutrons in the world of charge, they mean nothing. You get it? They mean nothing. So now, when we go over here and try to measure the charge here, and I'll write this down for you, but I'm in charges, and the SI unit for charge is coulombs. Now, the electron also had, oh man, 1.6 times 10 to the minus 19 coulombs. Huh, wow, you guys are like even. But they had a test, and they said, with this charge here, that one tends to be repelled by the plus field. So you must be minus. So you must have a minus that many coulombs, and you had a plus. But being humans, guess what they did? I could talk about coulombs all day, but they made it easier. What is the charge on a proton? I hereby declare that that many coulombs is what? One chunk of charge. One. And it's positive. So what'd you learn in middle school? Protons have a what? +1 charge. Oh. And what about electrons?
Hi everyone, I'm Christina, and I am here today with a
You
few
see that?
members from Rush. As Thanksgiving is approaching, we enter a season of thankfulness. We encourage you to be thankful for all the many blessings that the Lord has given you, and cherish the time that you have with friends and family this holiday season.
Hi, I'm Lindsay. Today I wanted to share a few things that I'm thankful for. I'm thankful for the opportunity to come to a school in person and be at a school that works hard to make sure we stay on campus and are healthy and safe. I'm also thankful for my friends and family and the joy that they bring me to my life. Psalm 69:30. I will praise God's name in song and glorify Him with thanksgiving. Colossians 4:2. Devote yourselves to prayer, being watchful and